All right, so thanks for coming. My name is Leszek and I'm here today to talk about great debugging. Thanks to Andrea for inviting me. I am honored to be speaking to you today. Before I get going with this talk, I hope you don't mind if I make a tiny little demographic survey. So how many of you, raise your hand if you are not in the games industry? Okay, that's not too bad. I was a bit worried that I might have a room full of game developers and they would just be bored to death with all this. So because with this talk I meant to target precisely people outside the games industry and just like shed some light on how game dev debugging is probably a little bit different from B2B or enterprise software development. And a little disclaimer, I've worked with medium to large games, so the following is based on my experience with such projects. So it might not be the same with smaller ones. So I represent a company which is called Nordic Games. It started in 2011 as a sister company to Nordic Games Publishing, known for a game We Sing for the Wii. Base IP, it's a game publishing company, so the base IP it acquired from Joe Wood and Dreamcatcher, and IPs such as Spellforce, The Guild, Aquanox, Painkiller. And we were initially focusing on smaller niche games, but since the acquisition of THQ IP in 2013, we've been ramping up operations a bit. And we are now shifting towards being a production company with internal developers. So since fall 2013, we have an internal studio in Munich, Germany, which is called Grimlaw Games. Who am I? I'm a programmer with Nordic Games, and that's a bit unusual position with this company, since it's a game publisher, so they usually don't do development directly, but I am mostly concerned with Linux ports. I still have, I will be changing companies soon, but for still a few weeks I represent Nordic Games. I had a short-lived freelancer gig in the meantime, and before that I was a generalist programmer at a Polish studio called The Farm 51. Where I worked on the games Painkiller, Hell and Damnation, and Deathfall Adventures in basically most of the departments. So here is the agenda for our meeting today. It appears a bit lackluster, but the devil is in the details. So I would like to lay down just a little bit of context before diving into case studies. This is a schematic for a typical game loop. It's like the core algorithm of most games. In the real applications it may be slightly different, but that's the gist of it. And so until an exit condition is met, there is an endless, infinite loop where you update the game state and then draw it. This draw block here is like an umbrella term for generating all of the game output, which is video, audio, tactile or haptic feedback, everything that the game outputs to the user. 33 milliseconds is how much time you have to get stuff done in a single pass of the loop. Though this is a simplified structural diagram of a modern game. As you can see, there are many components that need to do their own jobs, and you only have 33 milliseconds if you are targeting a 30 frames per second gameplay, or if you are targeting 60 hertz for super smooth feeling and low input latency, then you have even just half of that time, so that's very little time. And in game dev, programmers almost never work in a bubble with their own, with programmers. You just be working in tightly woven teams with people of diverse skills, because you have all those different job descriptions inside a game development team. Also, you have some severe fixed hardware constraints when you're targeting consoles. PCs are obviously more lax. You're only getting this hardware, you're not getting anything else. So it's not unlike embedded development. It's the most prominent reason for extensive use of native code in game development. Also, the trade-offs are a little bit different. So, while in enterprise software, say, you would probably be trading the cost of a project with its robustness or scope, then in game dev you are more likely to maybe trade fun for performance. So it's just different factors to weigh in. And games are indeterministic in a lot of ways and very complex. So this leads to poor stability, which makes debugging all the more important. You have parts that make no sense in isolation. So if you heard the term emergent gameplay, it's when you have unscripted interaction of different smaller game systems that produce interesting results. Then testing those little parts of those little systems that doesn't really have a meaning to it. So also, how do you even define correctness if you want to test for correctness? It's usually you cannot really measure fun, and even in technical parts like rendering, where you could do per pixel comparison of rendered scenes, there are still many factors that come into play, and it's similar for performance regressions because there are many factors like. With so many people working on, if the team is medium to large, with many people working on the game, there are so many things that can change and impact the per pixel results of the performance of the game that you would have to update the tests literally with almost every commit to the version control. And there is also a version to general software engineering. You will probably not find any UML modeling in game dev. Object-oriented programming we have this love-hate relationship with it. I mean, it's useful, it's easy, but at the same time, it's hated quite a lot. Same for design patterns. C++ STL is used rarely, if ever. Templates in general. There is this prevailing attitude that special problems need special and not generic solutions, and there is a lot of ego and elitist crap in this, and also the not invented here syndrome. But just take it with a pinch of salt. Okay, so moving on to bug species that you can encounter in game dev. This is not from any game I've worked on. I think this is one of the Call of Duty games. Judging by the fact that it's an SAS, but it just made me chuckle. The categorization of bugs that I'm going to introduce in a moment, it's nothing formal or canonical, it's just something that helps me make sense of my work. So of course you get the general programming bugs, memory access violations, dangling or initialized pointers, all that jazz. But apart from that, you also very often get bad math. So for instance, you can get an incorrect transform order. So transformations of objects in 3D space are usually done by matrix multiplication. Matrix multiplication is not commutative. So A times B is not the same as B times A. So you will just get something which is substantially different if you mess up the ordering. You can also mess up the transform space. For instance, if you have this model of a car and you wanted to transform it by 100 units on the x-axis, then of course depending on the space in which you apply the transform, you will get a totally different result. There are also the temporal, what I call temporal bugs, meaning bugs which are related to the to the passing of time, basically. So it's a huge thing in game development because most things in game are in some kind of motion, and so their state changes over time. And so this entity update thing, this pseudocode for a loop is again a schematic and not just something copied and pasted from a game code base, but it has it captures the essence in that you just have a huge loop that goes over all the entities or actors in your game and updates them. So we will get to a case where the order of updates is important. later on. You can also have bugs in interpolation and blending of things, like badly calculated alpha term or bad blending mode. And there are also something I call deferred effects, in which is basically it's basically asynchronous stuff that happens after a number of frames or after a number of time and some kind of condition is met. And the end also may be random, indeterministic, and that makes debugging hard. There are also the well-known graphical glitches. This is an image I found on the internet from early Battlefield Bad Company. So, you know, most graphical glitches result from incorrect render states. So, in the render state, you have the resource bindings, so textures, shaders, buffers. They might be you might be binding the wrong resors. The blending mode in the render state may be wrong. The tests for depth, for stencil buffers, for alpha testing and backface calling, you know, there's a lot of state inside of the renderer that you have to make sure is correct. Of course, in shaders you can make just the regular programming errors that you make in any other kind of code. And also there are problems which result from precision. Because, well, in graphics you cheat a lot, so you also often use low precision texture formats to store data, and well, that can also generate bugs, and also function approximations and stuff like that. And finally, there are content bugs, which are bugs which live like outside the code. It's in all the stuff that all the rest of the team, all the non-programmers create. So you may have an incorrect script, which can be code or graphs, like this graph. And you know, when you look at something this big, it's a flow graph. I think you are bound to, you know, with this kind of organization, you are bound to have some problems, to run into some problems. And of course, you can have the buggy assets, the media content. And I don't mean like substantially incorrect things like a human body with wrong proportions or a dog with 5 legs. I mean that they may be technically invalid, illegal assets, like mesh vertices with incorrect values or texture in the wrong color space, whatever. So this is where custom and domain-specific debugging comes into play. And the worst part of that is that usually it's almost never one thing that is wrong. You will get, because, well, most cases are 2 or more of the aforementioned bug species, and they are intertwined. So, for instance, you might get content bugs that manifest because of rendering glitches, or you may have temporal bugs coming out of bad maths, or threading issues resulting from bad content updated in a specific order, or all the other ways around, and all the while sprinkled with generic programming errors. So it's a quagmire. So on to the case studies. So most of the cases I'm going to discuss are illustrated by material captured by a quality assurance company called Quantic Lab, who are the contractors for those projects. I haven't documented all the bugs so well though, so I don't have fancy screenshots or videos for everything, sadly. But I have made a vow to better document the bugs in the future so that I can put blooper reels or something together. And I had a hard time trying to come up with an order to show the cases in. So, you know, I thought that maybe areas in which those bugs appeared, but then, you know, you have this overlap of areas, so probably not a good choice. And then chronology of those bugs doesn't make much sense either, because the order of discovery was also pretty random. So just try to maybe guesstimate a little bit how interesting they would appear to the audience, and that's the sorting key. So starting with really silly things and small ones like flawed logic of video settings menu, where the tester chooses his settings and then it's barely visible, but basically this setting just just isn't saved. So trivial things like that, or like this, where you get this like flash of where you suck the soul in, and after the flash, notice that the player wields a different weapon than at the beginning. So it's starting with things like this, or you have died, but since you were sprinting at the time of your death, and the player state is not correctly reset, the camera animation prevails. Of course, there are more interesting cases where debugging gets a little bit trickier. This is just a screenshot of the survival game mode. It's sadly not an illustration of the case. As I said, I don't have documented everything. And this game mode was programmed mostly by an intern and had some custom death logic so that living players can help and revive those who died. And when a player really actually died, they would be teleported into a seemingly random point in the map, like the corpse. And so after the intern could not fix the bug for 2 weeks, I came over and tried to help him out. So just to explain the context a little bit, this is totally not visible, not good. But in normal gameplay, pawns meaning the game world representation of characters, will have some simplified movement where you sweep the actor's collision primitive through the world. So like the default in Unreal Engine 3 is a cylinder. You cannot really see that, but there is a red frame around the character. And then when you sweep that collision primitive, you slide it along slopes and stop against walls, stuff like that. But then, once the pawn dies and you want to get Raggle, then you just switch to physics-based movement, where the physics bodies control all the body parts. And this screenshot is also very barely visible, but it shows the partition of a character for the Ragdoll bodies. And the thing is that physics bodies have separate state from the game actor. So the whole game actor does not drive the physics bodies per se, unless requested. Well, and some other cases that I don't want to delve in right now. But if the actor is driven by physics simulation, then their location is synchronized to the hips, bone, bodies location. Yeah, there should be another location word. And this is, something that already gave me an idea of what this bug may be. I ventured a guess that it might be that the state of the physics bodies is still left uninitialized after the spawn. And I had this idea, okay, let's maybe put a breakpoint in the function that moves actors to the world octree. But this function gets called a gazillion times per frame for all the different objects that don't move in their very close neighborhood. So that gives us terrible noise. And then let's try a breakpoint condition. But how do we formulate the condition? Like, we get a teleport from arbitrary point A to arbitrary point B, and there are other actors which are being teleported this way throughout gameplay. So this was also a no-go. I was thinking that maybe distance, but and then just the obvious solution is that we just make a sequence, so we break on death instead, and when the breakpoint on death is hit, then we make actually the breakpoint in far move, and then we just can catch it, and that revealed that the physics body was indeed driving the actor with out-of-date state. So the fix was simply to request the update of the physics bodies before switching to Ragdoll. There are also Heizen bugs in game dev. This is unfortunately a photo of a TV playing the game, but that's just the kind of media that we got from QA. It's still better than nothing. And if you look at the weapon here on the left side of that screen, it actually should be in this area, in the bottom right corner, but for some reason it's floating mid-air away from the player. So that was very interesting. You can actually see this in motion here. See that weapon just, he's going to switch weapon. It's barely visible again, low contrast, but it's basically kind of, as you turn around, you can see that it just lags behind the player. And if you just turn to the front, it just goes below you. And you know, it was something that we had a very low reproduction rate for that, and we only encountered it on consoles, so it didn't happen on PCs, and particularly never on developer machines. This includes the dev kit consoles. So on test kits it did happen, on dev kits it didn't. But the thing is that the player pawn was in a special state for that roller coaster ride, and many things could go wrong because of that state. And for the lack of reproduction, I just sprinkled the code with debug logs and you know, just put a QA tester on, you know, just play this level for 100 times and just grab me the logs. And strangely enough, this worked. So that was a little bit of a shotgun debugging thing, and you know, it just in printouts, in the logs, it was evident that the update order for the two entities were reversed in the cases when the game was bugging out. So upon closer inspection, the player pawn forced to update after the roller coaster car, so that, you know, like, look at this loop. If you try to read the state of an entity with an index which is greater than the one we are currently processing, we are looking at the state from the previous frame. So it's not up to date. So that special state forced the pawn to update after the roller coaster, so that the player does not lag behind the roller coaster. But I did not enforce the same thing for the weapons, so it was possible that the weapons would be updated before the player. And that was basically it. So I just enforced weapon update after player pawns. And the mechanism to enforce update order are beyond the scope of this talk. It's game engine specific. Another funny thing. Oh, again, not visible. Okay, I'll try to describe it. Yeah, characters with rapiers. Well, when we are putting builds together for the publisher and so on, we noticed that some characters, but just some of them, had one protruding vertex from the mesh, which would, like, you know, go from their hip to the back, and it kind of gave us the impression of like a sword over a rapier or something. So that's what we called it. But of course, it had to be fixed. So Unreal Engine 3 has this content cooking thing as part of the game build pipeline. So all the redistributable builds are cooked builds, and this is why this bug never showed up in developer builds, just in the redistributable ones. And yeah, and upon inspection, we could see that the logs contained assertion messages for out-of-bounds vertices, and that led us to the merge vertex compression scheme. It's a very simple one that gives you about 50% savings. It basically normalizes the vertices to a bounding sphere and just maps the -1 to 1 range to signed 16-bit integer. Yeah, and this is the assertion. It's again a paraphrase. It's not verbatim from the code. It's just a paraphrase, but it was more or less like this. So for every component of the normalized vector, it would just check if the component is within the accepted range, and of course we're hitting that assert, so one or both of those comparisons had to fail. No, actually just one. If one fails, then the other one is not even executed. Oh, the funny thing was that the component in question was not a number. And the interesting property of none is that all comparisons fail, even with itself. So yeah, we were like, how did it even get there? And actually, I tracked the NAN all the way down to the raw engine asset, and yeah, we are still wondering to this day how it even ended up in that place. I don't know. Maybe it was a stranded neutrino or cosmic radiation. Something, but we just re-exported the mesh from 3D software and it worked magic. Yeah, and sort of a meta case, when I was investigating that previous thing, I hit an assertion in a texture compression library, which was binary only. We didn't have sources for it. And so I was flooded by non-critical assets, and for almost every texture there was something with mip maps, whatever. But I just could not ignore them, you know, mass ignore all of them, just don't show me this crap anymore. So that really was terrible noise, and we had really thousands of textures, so But at the same time, I just so happened that I was reading a blog by a fellow Polish game developer, game programmer, Maciek Siniło. There's a slide with references at the end, so if you download the slide deck after the conference, the links are all there. So he had a blog post about coding in a debugger, and the solution for this precise problem that he offered was to enter this assembly, locate the function that displays the asset, and take note of the address where that function is, where that instruction is located. Then we enter memory view, look at the address, and we can verify that this is indeed the address by seeing that hexadecimal E8 is the call opcode for Intel E386. And since it's running in virtual mode, then the argument is 4 bytes long. And we just knock it out, so replace all those bytes with hexadecimal 90, the NOP opcode, and voila, the call instruction is not there. Of course, this only lasts until the debugging session ends, but it did the trick. It has upsides and downsides, because obviously even if you break something, then you can just break the debugging session and just restart it all over. But of course it gets tiring when you have to do this, when you have to repeatedly restart the experiment. But there are more examples of tricks with editing live code, so I recommend checking out this guy's blog. The link is in the reference slide. Also, another thing, the game Painkiller Hell and Damnation was a remake of the original from 2004, and I was tasked with closely replicating the player movement physics in this new engine. The original game used a different engine. And as you could see, the player walks through the level, then jumps into a tight space, and subsequently gets stuck. They cannot move anymore. So so the first version didn't work very well. And here, if you look at the bright things, you can notice that the camera is jittering to the side. So it was also moving a little bit without player's intent. So clearly there were some things which were wrong. Then again, the context. So we are recreating player movement from one engine in another. So different games engine meant, for instance, that there were different measurements of distance and velocity. And it may sound absurd if you think that physics as a strict science, but the different physics engines, actually physics simulation engines, will behave absolutely differently even with the same data. And that's beyond the scope of this talk, but it's just this: you can rely on the physics simulation engine that it will do the same thing as the other engine. So there are many nuances, like gameplay nuances that you have to sort out, like air control, jump and full heights, whatever. But also this slope and stair climbing. So in the original game, when you would stand on a slope, you would just start sliding down it. And this wasn't the case in vanilla Unreal Engine 3 physics. The main nuance, the main difference was that Unreal Engine 3 by default supports cylinder collision, or even box actually, and not cylinder. And Painkiller, the original one, used a capsule, and as you can see, capsule has the hemispheres, the smooth hemispheres at both ends, and so you can probably imagine how it performs more smoothly than a cylinder on uneven terrain. So switching our pawn collision to capsule was not an option because we were tied on a tight schedule, and that would be a quite drastic change in the code base. So I just kind of hacked it up by emulating, by sampling the ground under the cylinder instead, to just try to emulate this slipping force by you would have those. I would just have those samples, and when they don't hit ground, they would contribute to a slip force vector, and then this vector would be applied and just pushing the capsule to the area where it has pushing the cylinder to the area where it has less ground coverage. And there is no clever way to debug player movement that I found. So like the best thing I found was just to put the game in slow motion, then get it to bug out, and then just break in debugger. And that was usually more than enough to actually find the source of the bug. So the situation when getting stuck, it turned out that it was something like this. We had if the green thing is the bottom of the player's cylinder, then the black diagonal lines are slopes with non-walkable surfaces because they are too steep. And the vanilla UE3 code sent a player in that situation into the folding state where they had some control, and in our case they didn't because of how Painkiller worked. So the fix was to keep the player walking in such a specific situation. And moving without intent was, I added some visualization of the sampling of the ground below the capsule, and turned on the collision display, and then it was clear that the cause was on the sampling. And so the situation was like on this diagram, there were like 3 things protruding from the ground, so you can probably see how if green things are where the ground is not detected and red where the ground is detected, then on the left you can probably see how this can start an oscillation from one side to the other. So this is precisely what was been happening. So I just fixed this by increasing the sampling resolution. I just added another ring in the middle, and we didn't have any more reports of that bug. And I know this is a terrible hack, but it just got the job done, and I could focus on something more important. Another gameplay-related bug, we had full-screen damage effects, as most games do. And there was one specific level in the entire game where those blood effects would periodically disappear for a second or two, and that was quite mysterious. And the post-process effects in, Unreal Engine 3 they are just a one-way chain. So on the left you have the raw scene texture, and it just goes from the left to the right through the chain. All the effects on the way just run and alter the texture, and then what's on the right gets displayed. And there is actually no debugger in Unreal Engine 3 available to observe the post-process chain. This is badly visible again. But basically I wrote my own debug overlay that walked and dumped the chain contents, and so I basically, it's kind of like an ASCII art thing, so it would use the Unreal reflection system to inspect the parameters of all the effects, and it would just dump them, and where it made sense, it would even use progress bars. So you would get visual feedback, and the best thing about this is that you could basically track what was happening over time, and this is what was important. Because then it was evident when using this that something was overriding the entire post-process chain, because for the moments where the blood was not visible, you could tell that all the effects were switched off, and the only thing that could have switched everything off with one swift stroke would be a chain override. So I just put a breakpoint in chain setting function, and it turned out that it was a level script, so an overeager level designer just ticked one checkbox too many when setting up thunderstorm effects. So I just disabled chain overriding altogether, because with the way that we've been managing post-process effects, we had no use case for that option anyway. So yeah, and animation, please. Why is this so dark? But if you pay attention to this character's torso from the waist up, you can see that he does something weird when reloading. So he basically does a 360, during that blend. So you get stuff like that. Then you also get some not as severe screw-ups like this, where the hand does not match the weapon, or here where it kind of does match the weapon, but instead of holding the magazine in the vertical position, the hand is like this. So you can also get incorrect animation states. And in UE3, animation is done by evaluating a tree. A tree can look like this. This is from the UDK documentation. And sequences, and the branches are weight blended. So you can get either a replacement or an additive blend. Then you can, basically just evaluate the tree. And I think it's a prominent case for domain-specific debuggers. So there were no tools for debugging that in UE3, so I also wrote my own visualizer, which is, as you can see, kind of related to the PostPersist one. This allows the inspection of animation state, but not exactly the reasons for the transitions. So that still required traditional debugging or just dumping call stacks when the transitions happen. And yeah, again, it walks the animation tree and dumps the active branches and its parameters together with weights and other parameters that make sense as a progress bar. So we were developing our own animation system, and it grew organically, so it was not very well thought out. But at one point, we had so many bugs that we sort of developed this animation bug checklist. So first I would just inspect the animation state in slow motion and just like seeing if it's even in the right locomotion state. Seeing if the blending mode is used correctly, or if the AI in cutscene state was not doing something weird because it was also capable of overriding animation altogether. And at the end we also had to inspect the assets, because it's happened many times actually that the root bone was not correctly oriented, or its motion was incorrect, and also then inverse kinematics. Are the targets for IK even present? IK is a technique where you kind of work out the positions of the body, not by of a bone chain, not by following a hierarchy, but you get an endpoint and you try to put the hierarchy in such a position so that it arrives at the endpoint. And even we would have to check if the mesh skeleton for the given character was complete and correct, because it also happened that it was missing a few bones and things were not working. So for this particular bugs that I've showed at the beginning, for the first one there was bad root bone orientation in animation sequence, and since it was only played from the waist up, that's why it was only the waist that was doing the 360. When the left hand was of the weapon, the inverse kinematics was off, so I just had to revise and fix the state control code. And for the last one, the IK target marker was not oriented correctly in the weapon mesh. We're running out of time, so I'm just going to sprint through the last few ones. This one's slightly newer. It only happened this year in porting Darksiders. There's a section in the game where you have portals, like in the game portal, that can be used for fast traveling and puzzle solving. And when they would be in view, you would get this invalid aspect ratio thing. So I had to do some graphics debugging, and graphics debugging is basically just trace and record the graphics API calls to a file or to a buffer, whatever. Then you replay the trace, and you review the render state and resources at different places in that trace. And the trace may be somewhat unreadable at first, but that's why you use annotations, and you can annotate them for clarity. There are tools in both Direct3D and OpenGL for that, and if you are interested particularly in OpenGL, shameless plug, I did a talk about this as well this year. So quick render state inspection revealed that the viewport dimensions were off, and I found it was 1024. I was thought, is this from Shadow Maps? And then I found the last call where the viewport dimensions were set, and it was from the Shadow Map code indeed. So why wasn't the viewport updated for main scene rendering? Basically, render state changes are expensive, so you try to cache them. But when the cache and the actual state diverge, then you get bugs, and that was the case. So basically, the port was based on Direct3D, and I kind of assumed the Direct3D convention where the viewport dimensions are part of render target state and not global state. Yeah, just tied the viewport dimensions to render target in the cache, and that fixed it. You can also get multiple kinds of black artifacts. These two that I've just shown were from the PS3. This is from NVIDIA on Linux. you could see those black squares when the skeletons were spawning. These were also on NVIDIA on Linux. And the newer one, this whole thing should be like something of more of a fog than a black dome over a building. So the first thing I do with this kind of thing is to inspect the state. But since I found nothing suspicious, I mean, this thing actually repeated for every one of those bugs. So nothing suspicious found. I turned to shaders. If I was using a newer version of OpenGL, I could have used the NVIDIA's Nsight debugger and just debug the shaders like normal code. But since I was an older OpenGL, I was using the Your Mom's debugger, which is just dumping debug values all over the place and seeing if that gives us an idea. So I was just shotgun debugging with different inf, isNone, whatever functions, and isNone returned true. So the thing is that so there are some conditions under which the implementation of the power function is undefined. And NVIDIA returns the QNone the barbarian, while most other vendors just return 0. So it was just a question of fixing the power function calls. And the last thing I wanted to show today was this place in Painkiller Hell and Damnation, which you also probably can't see because it's too dark. But there is an entrance to a cellar, and this place gave me the creeps for weeks because basically we had a totally wild crash when entering that cellar door. We had the game in content lock already for a while, and the PlayStation 3 port was almost done, and we had a crash about 3 to 5 frames. This amount of frames differed from repro to repro after entering that specific room. And the first report included a perfectly normal call stack, but there's no obvious reason. I mean, the call stack was not corrupt or anything. It was just weird. And QA got reassigned to another task, so we could not pursue that more. So I concluded it was just an out-of-memory crash and just waved it off because we were still optimizing. But the bug came back and with a wildly different call stack. And I asked QA this time to reproduce it multiple times, including other platforms, and it did not happen on anything but the PS3. And the call stack was just totally different each time. And I asked my colleagues for opinions, but we could just take shots in the dark. Is it an OOM? But it even happened when we increased the amount of RAM to 512 megabytes, because normally in retail you need to get 256. So we still were getting the OOM. That doesn't sound good. So yeah, some other options, and after the initial confusion blew over, I figured it's just best to review the hard data that we had. So I just took to a larger sample of call stack, and I noticed that most ended in dlmalloc, which is the allocator that UE3 uses on PS3, in its integrity checks. So it's assertions triggered upon allocations and frees. Not all of them, but like the majority did. And I was like, memory stomping, could it be a real bug for real men? And then the thing is that I've never done memory debugging before, so I needed to do some research, and Sony doesn't provide any tools for this kind of thing, but I intended to use some debug allocators which work with memory fences, so they reserve additional memory between the allocations and watch what happens with that memory. But it was difficult to hook up to Unreal Engine 3, and finally I found and integrated a community developed tool which is called Heap Inspector. It's a memory analyzer, so it's not the best tool for the job. It's focused on consumption and usage patterns, but it was easy to integrate, and it captured call stacks for all the allocation reasonably fast. So several reproduction attempts later, I noticed that there's a correlation between the crash address and the construction of a specific class. So that was it. And again, a paraphrase, this is Unreal script, so it's a managed language in the virtual machine. So at the top, we have a class declaration, which basically all it does is that it has an array, so it has a considerable size. And in some ammo consumption code, let's say, in a weapon, we just had yeah, have this code at the bottom. And the trick here is that this line at the bottom is copy construction. So basically, you create a new object of class actor component with the object crash as a template. Yeah, so this is the culprit, and this is actually a buffer overflow. So the VM did not check for if the buffer is large enough. Well, does the mic work? Okay. So the VM did not check if there was enough space in that buffer. Yeah, so the lack of manifestation on X360 and Windows was due to a larger allocation alignment. So on the PS3 we had 8 bytes, on Windows and X360 we had 16 bytes, and since this particular class did not have 1024 integers but just 2 or 3 new fields, it was enough to fit in that allocation alignment. So this is why it never showed up on those other platforms. So the fix was simply to actually check the class hierarchy on copy construction. And I wish I had Valgrind. It's a great memory debugger, and if you want a good memory debugger tool, so I also made a talk about Linux game programming, but it also includes a section on Valgrind. So it's a very good tool to use for memory debugging. And time for the takeaway. So in game dev, time is of the essence. So one thing is that we are on tight schedule. The other thing is that we are constantly in motion. So where in debugging, some kind of temporal inspection tools is the key to fixing maybe not most, many bugs. And we will often still need custom domain-specific tools because we come up with our own environments, workflows, whatnot. It's also complex and deterministic, so it's difficult to automate testing, which could probably early detect some of those problems. And quite wide knowledge is required, even if superficial, then you still need it quite wide to, if you are supposed to successfully fix bugs. And also games are prone to bugs outside of the code, so again, the custom domain-specific tools. Rendering as a whole is a separate beast, so it has, it's totally separate ecosystem in isolation from the rest of the game, actually. And they are still far from ideal usability, but the rendering debugging tools are improving, so it's actually starting to be fun. And it's good to know your machine down to the metal, because if you make a large enough game, at one point you will go down to disassembly. At least that's my experience. There's just no way to escape that. And what's related to that, good memory debugging tools make the world's difference. And finally, you are never safe, not even in managed languages, because you are only as safe in managed languages as the VM is. And that's pretty much everything. If there are any questions, that would be the time. I hope I did not bore all of you to death. Okay, so I don't see any hands raised, so I guess if you think of anything, we can just meet somewhere in the lobby or whatever. So thank you very much, and this is everything. Thanks.